Hi, everybody. Welcome to the Google Meet version of pre-calculus. I hope that this new system, I know it's not as good, but hopefully it will meet our needs. I have here, one thing about Google Meet is that I don't have the ability to mute people. So just you'll have to do that yourself. If you look up at the screen, you can see the aim is about transformations with polar graphs. And hold on a second, what is that? Am I muted? Hold on a second. Okay, thanks.
No, you're not.
So just as a refresher, look at what happens in rectangular graphs when these various transformations, see questions 1 through 6, what's the effect of doing these transformations on the graph? What geometrical transformation happens? So you could take a minute, you could type into the chat what happens in rectangular coordinates when you do these various transformations. Okay, so you can start typing stuff in about 1 through 6. What's the effect of altering this function? Oops. Back to here. Okay, so what happens with number 1? What's the effect of number 1 is a translation. I see Emily moved A units up, so that's right. How about number 2? I see Talia said it's a stretch. Specifically, what kind of stretch? It's not quite it's like a dilation, but not exactly. It is a vertical stretch. It's not exactly a dilation because, like, if you took a circle, for instance, or even a parabola, it becomes like a skinnier looking parabola, whereas a dilation would keep the proportions the same. So 2 is vertical stretch. Number 3, I see here x-axis reflection, Youssef says, and that's right. Like, if I always picture a parabola when I'm doing these, so it like flips it upside down. How about number 4? I want to write it into the comments. Anyone thoughts about number 4? You could use a specific example. Now, the parabola, okay, that's not good. You know, if you take y equals x squared and you replace the x with negative x, it doesn't seem to do anything. It's the same graph, but it actually did do something. What does replacing for number 4 x with negative x accomplish on a graph? I'm not seeing much chat. Anyone able to chat? Oh, I see. Sorry, everyone. It did not scroll down for me, so I was looking there. But yes, it is a reflection over the it is a reflection over the y-axis. Might be better to use a graph that's not symmetrical about the y-axis to visualize that. For instance, y equals x cubed. When you replace the x with negative x, it turns into that, so we can see that reflection better. And how about number 5? Yes, and that is shift over, in this case, to the left by a units. And how about number 6? Compare that to number 2. And that's right. It's actually a horizontal, I mean, technically it's a horizontal, it's like a stretch, but it actually shrinks it, it like compresses it. So a stretch, you could have a stretch by like a fractional factor, but just to tell the difference between which is which, we'll call that one a horizontal compression. So we have vertical shift, we have vertical stretch, we have a reflection over the x-axis, we have a reflection over the y-axis, we have a horizontal shift, and we have a horizontal called a shrink. I've heard different things for those: compression, I'll just say stretch, and shrink. Now, what happens when we do this with a polar graph? So here I have the same 6 things, and I'm curious, here I call it like f of theta instead of r equals f of theta equals 2 sine theta plus 2. So I have the same 6 things happening, but what do you think that does to the graph of a polar graph? And for this one, I don't know if I can pause my recording. I want to give you like time to think about this. I'm going to try to pause the recording. Anyway, you could do all kinds of chatting. So would you make some theories about what some of these might do geometrically? What do you think happens if you put an a in front of a function? What does that do for polar? Think about that, talk about that, chat about it. Okay, I've seen a lot of good ideas in the different about the different numbers. Um, for number one, type in what did you think the answer was for number one? This was the thing that was like a vertical stretch for rectangular. What is it? What do you think number one was? Looking over the comments, I see dilation. And in this case, it is a dilation, an actual dilation. Here's a little picture of one. It is an actual dilation. It is the same proportions as the original, unlike in a rectangular where it's more of a vertical stretch. Okay, how about number two, negative f of theta? Officially, what do you think that one accomplishes? And I see Anna said reflection over the x-axis. I see a couple for that, but then I also see Willis said it might reflect over the origin. Well, in one sense, both people are right in that it does look like it's reflected over the x-axis, and it looks like it's reflected over the origin. But the official answer to this one is reflection over the origin, because if here I have a point, that's r theta. When I put this negative in front, the same theta causes the negative r. So for number one, this one was a dilation. For number two, it's officially a reflection. Some people say in the origin or in the pole, or you could say over the pole. Okay, how about the third one? F of negative theta. I hear someone's microphone. I know people miss Zoom, but apparently it's really bad what it does. Like hackers can not just watch a math lesson, like who cares if they see my pre-calculus lesson, but they can like, you know, steal your identity or something and become you or something like that. So we had to do away with Zoom, as good as it was. Maybe they'll fix Zoom eventually. But it is, I see Youssef wrote x-axis reflection. And yes, even though the picture is the same as the last one, this one is going to be officially an x-axis reflection. Now, here's a real interesting one, the fourth one. What do you think for when you add a to the angle? There's some. Someone's microphone is on. Oh, people can tell who? Melissa, how do you know whose microphone is on?
She pops up right under your screen.
Oh, I see. I don't have the screen. I just have the chat because I have so many windows going on. Thanks. Okay, great. So how about number 4? 4 is like the most important of the questions, I think. And I saw Talia say rotation. And that is exactly what happens. When you do a plus alpha, it rotates the whole picture by alpha degrees. And that's because, let's say that alpha is like 40 degrees. When you put in f of, when you put negative 40 into this new graph, it ends up in the same place that zero used to be. So, oh wait, this is reflected by a lot more. This picture is reflected by a lot more than 40. It looks like it's not quite 180. It's more like 140. So when you put 140 in, what used to happen over here is now happening. Am I rotating the right way? Yeah, it is. It's a little confusing, but it does a rotation. Because when you put in the negative of the angle, it ends up where it used to be. So I guess it's this thing ends up, there it is, over there. So now when I put 140, I end up with the thing I used to get at 0. So that's pretty interesting, because that means that you can take even a really complicated graph like r equals ED, let's say 15 over 1 minus sine that, you might remember, was a parabola with focus at 0, 0 and directrix at y equals -5. So if I were to just change this, if I want to make a rotated parabola, I could just say plus 30 degrees, and I'm going to end up with something like that. Everything's going to rotate. The directrix is going to rotate also. So rotation, which is very difficult in rectangular, is actually very easy in polar. Translation, which is very easy in rectangular, is very hard in polar. There was a situation where we had something like this. You might remember we had a long time ago line like this that was tangent to this circle, and here's like the point, like 5 comma 45 degrees, and the equation was something like r equals like 5 over cosine theta minus 45, something like that. You can see now that the minus 45 rotated what would have been a horizontal line, r equals 5 over cosine theta, is the same thing as r cosine theta equals 5, which is x equals 5, sorry. So what would have been x equals 5, which is a vertical line, putting in this minus 45 turns it into a slanted line. So rotation, easy on polar. Now, what happens when you put a coefficient in front of the a? You want to type in, that does some kind of weird stuff. What kind of curve does it turn into? Like in this case, if I stick a coefficient in front of the theta. Okay, I'll put it up there. It becomes a rose curve. And the last one doesn't really have a name to it even. It's kind of weird what it does. It distorts the picture. Every value gets, every r value, so there was some r value, and it gets increased by a, So it kind of like stretches out the picture, but it turns into something that's like not proportional anymore. You could see the way that those a's are all equal to each other, but by adding a to each thing, the thing that was 0 turns into a, which is, so this thing's not a circle, you know, but it distorts it in a weird kind of way. Someone asked about f of negative theta. That one was a reflection over the positive polar axis, or the x-axis, the way we talk about it. Okay, so that's the first thing I wanted to show you today. That that's what happens with uh, with transformations of equations and how they affect the graph in polar. Tomorrow is actually the last day of polar, and I have a Kahoot that I made, which I'm either gonna, I feel like doing it tomorrow instead of today. So if you want to like study for the Kahoot, kind of like a all the stuff up until tomorrow, if you want to win the Kahoot, I'm going to do that tomorrow along with some other thing. But the rest of this, so the main part of today's lesson is this, the different transformations. But there's something that I want to show you that I probably could have shown you long ago, and I just didn't. So I want to mention it now because it's related to what's on the homework. So you may get some kind of really unusual equation that's in rectangular form, and we want to change it into polar form. Well, changing from rectangular to polar is particularly easy because you can always just change x into r cosine theta and y into r sine theta. And if you ever notice an x squared plus y squared, you can replace that with r squared. So I could take something like 21 and some kind of hyperbola, but if I just change it into 20 r cosine theta, r sine theta equals 1, it turns into r squared over 1 over 2 cosine theta sine theta. I can actually go one more step with this. Anyone know what? There's like one more. I could go one step further. Not that I really need to. This is a perfectly good answer. R squared equals 1 over 2 cosine theta sine theta. But something unusual, like surprising, happened. Does anyone know? And besides taking the square root of both sides, for instance, this thing, this denominator, does that ring a bell? Yes, Willis-Stroke. That's the formula for the double angle for sine. So I could change this to r squared equals 1 over sine 2 theta. There wouldn't be a real compelling reason to do that. Now, going in the other direction can be a little bit tricky. You're going to basically try to find a way to turn r cosine theta into x and r sine theta into y. So like this question number 8, if you multiply the entire equation through by r, minus 3r cosine theta equals r squared, then I could replace the r sine theta with y and the r cosine theta with x and the r squared with x squared plus y squared. So those are like things to be on the lookout for. This number 11 is kind of interesting. Someone want to type in what's going to be the key to getting your foot in the door for number 11? Yes, Riley says double angle formula. And on cosine 2 theta, there's actually 3 double angle formulas for cosine 2 theta. Yeah, I don't think it would matter which one you used. Let's say that I just wanted to use the r equals 3 parentheses 2 cosine squared theta minus 1 version of it. What am I going to need to do now? Because I'm kind of like, I can multiply the 3 through, but I'm like running into trouble. 6 cosine squared theta minus 3. What do I need to do so I can go like further with this? I need to get x's and y's into here. Where are they going to come from? What do I wish was in front of the cosine squared theta? What would be what would be nice if it were there, even though it's not? You could type it in. Remember, our identities are x equals r cosine theta and y equals r sine theta. Yes, Veronica and Nicholas say r, but go a little better than that. R squared would be even better because of the cosine squared. So if you multiply both sides by r squared, this turns to r to the third, this turns to r squared, and then I can proceed with this question because the r squared cosine theta squared would be the same thing as x squared. But this r cubed is a little weird. I'm going to leave it, if you don't mind, as r squared r, because the r squared is x squared plus y squared. I have a couple of options here. R I could write as the square root of x squared plus y squared. Maybe the best thing to do is to write this r to the third, write it as x squared plus y squared to the 3/2 power. That way it's like x squared y squared times the square root of x squared plus y squared. On the right hand side, I can say 6x squared minus 3. If you look at number 15, this is the last question of today. Look at number 15. What do you think is going to be the key to making some progress on number 15? Yes, and Riley says subtraction formula, and that's right. So we're going to say r, I'm going to write brackets, cosine theta. The formula for cosine A minus B is cosine A cosine B plus sine A sine B. And this becomes r times cosine theta times square root of 3/2 plus sine theta times 1/2 equals 2. See, this r out here is nice because I could just distribute it through. And then the r cosine theta turns into x, and the r sine theta turns into y. So those are some more complicated like equations. Like we have no idea what they look like. Some of them might be ones that, like for instance, this one, if I divided both sides by this, it would actually turn into the r equals 2 over cosine theta minus pi over 6, which actually was from the second day a line that does not go through the center. But even if you had no idea what it looked like, we'd be able to find the equations. Okay, so that's what I wanted to show you today. Tomorrow, there is going to be a Kahoot. So you could be ready with, you'll need a computer to display the Kahoot questions, and you'll need like a phone or something to answer the Kahoot. Also tomorrow, we have, we'll do the Kahoot first. That'll be the fun part. And then after the Kahoot, we'll do a pretty challenging thing that I like, which is where I give you like unusual curves and describe their properties and have you try to create equations from them. It's kind of hard, but it is like it's a challenge, and it's one of those sort of satisfying challenges when you figure it out. So, and then we'll be done with this unit tomorrow, and we'll move on to the next unit. Does anyone have any questions about today's lesson? Let me stop the recording. Hold on a second. Okay, recording stopped.